Hello and welcome to today's webinar about virtual closed-loop test of protection devices, testing with Cyprotec Digital Twin and Omicron Relay SIM test. My name is Nina Hühn and I'm promoter for differential protection. You may already know me from our 7SS85 webinar series, but today I'm not the presenter. I have the honor to guide you through this webinar. So, why virtual testing? What can you simulate with a protection digital twin? What are the benefits of system-based protection testing and how to combine both for a virtual closed-loop test? A lot of questions that I'm sure will be answered in today's session. We have two experts here presenting the topic. I start with our guest, Mr. Florian Fischer. Hi, Florian.
Hi, Nina. Hello, everybody.
Florian works for Omicron and he's the responsible product manager for the system-based testing solution Relay SIM test. Our second presenter is Mr. Cedric Harrisburu. Welcome, Cedric.
Hi. Hello, Nina. Hello, everybody.
He is a colleague of mine and the product manager of our Cyprotec Digital Twin solution. Of course, you will have the chance to ask questions. You can type your questions in the question field or in the chat during the whole webinar, and I will be your voice and read the questions to our experts. We will have a Q&A session at the end of the webinar. All the questions that we won't answer today will be answered after the webinar in a written format. So please don't hold back, ask everything you want to know. And yeah, now I'm happy to hand over to Cedric and he will start with the first part.
Thank you, Nina, for this introduction. It's a pleasure for me to have the opportunity today to present with Florian this very first webinar on virtual closed-loop testing with live demos. Why are we doing virtual testing? Will be the first part of the agenda today. And we'll continue what can you simulate with protection digital twins and how to easily perform open-loop testing with a Cyprotec Digital Twin. On the second part of the webinar, Florian will describe what are the benefits of system-based protection testing with Relay SIM test and how to combine both digital twins for virtual closed-loop testing. And at the end, we'll be glad to answer your questions. But first, let us start with why virtual testing. Why digital twins for energy automation? This is the answers to many problems you are facing today. One being how to validate as early as possible my protection settings. How to decouple the hardware delivery times and panel production time to test earlier the systems. How to reduce the time of the factory acceptance test or the site acceptance test on site as much as possible. And how to train your team more efficiently with the right tools. And last but not least, how to interact fast with experts, having your tools, your products, your configuration wherever they want. Those questions are answered with virtual copies of products and systems connected individually or interfaced as an ecosystem. And in the first part of the presentation with Cyprotec Digital Twin, I will introduce you the possibilities of our digital replica of a protection relay. It enables hardware-free testing for any Cyprotec 5 type device and any firmware version. It saves time and resourcing. Protection relay configuration can be pre-tested even before equipment ordered and delivered. It's possible to test the programmable CFC logic, to test your 1650 GUs, to replay power faults for faster troubleshooting, and perform virtual closed-loop testing. And finally, it's also able to integrate with external softwares or third-party hardware devices via VPN. The journey with Cyprotec Digital Twin has started 4 years ago, and we are continuing to deliver more value to our customers around the globe with various applications, starting with virtual factory acceptance test, virtual trainings, power fault investigation, etc. Many webinars that we organized at Siemens the past months were showcasing Cyprotec 5 protection devices with CPROTECT Digital Twin to perform any protection test. And last year, we had also a larger first digital twin webinar showing the capabilities into an ecosystem. But today, it will be more practical, as many of you are really seeing the potential first when they see it into action. So let's jump into the real virtual world. How to onboard first in 5 steps. First, you open your existing DXC configuration containing your CPROTECT 5 devices. There you export your simulation data. You log in into our CPROTECT Digital Twin application, import the simulation file, and interact with your simulated devices in just a couple of minutes. How does it look like with the tools? Exporting of the sim file from a DXC is a very simple step. You just select the project level, which devices you want to export, one, multiple, or all devices, and export that content. If you are new to DXC 5 and are interested to discover it, I've inserted a QR code with a download link to try it out for free during 30 days. Next, you have that simulation file. You log in into our CPROTECT Digital Twin application with the easy remember URL, cprotect-digitaltwin.siemens.com. It is supported by the most common web browsers. And the first time, you can register with your corporate email, create a multi-factor authentication, and practice a bit with a basic demo project. Once you logged in, the first page you see is a device list that you need to populate by importing your simulation file, where you browse the content of your local disk, find the file exported by DXC, upload it, and all devices that are part of that file are showcased in that list. Then simply select the devices you're interested in simulating and start them. Depending on your license, up to 20 devices can be simulated at the same time. Then you can see the simulated devices and operate them via the front display. The navigation is exactly the same like in a real device. And after that quick introduction how to onboard, let us have a look at how to simulate process data to feed those simulated devices with real process inputs. And there are multiple ways to feed the CPROTECT Digital Twin with process data. The first options we will see in the live demo will be with static inputs, injecting static analog currents and voltages, as well as binary inputs. The second options will be injecting transients with ComTrade, and finally with states sequences. So let us go now to the demo on the screen. So here you recognize I've already logged in into the application. As stated before, I uploaded a configuration that consists of 3 devices, our CPROTECT 5 Compact 7SX800 and 2 Universal Protection Relays 7SX85, one acting as a merging unit and the other one acting as a protection device protecting 2 bays at the same time. One bay will be protected conventionally and the second bay will be protected via process bus application, getting the value from the merging unit. So once those devices are started, you see in the user interface the different devices that are prepared. And the static injections we're talking about is on the left side, where you recognize 2 tabs, one for voltage and currents to inject voltage and currents, as well as binary inputs to set the status of binary inputs of circuit breakers, for example. And here in the test, where I configured already nominal values that you can see on the screen of the front display, let us just simulate a a simple trip on the phase C, the overcurrent application. So I have a threshold configured to 1.5 amps secondary value. I go over that limit, and what is happening is the device is reacting to that static input value and is tripping, as you can see, in around 300 milliseconds. You get the trip time on the front display, which corresponds to the configuration setting set into the device. The same way you can control the injection of any device. It was with Spray 5 Compact. Now let us see the example of the protection device protecting two bays. We'll perform two tests. One protecting the conventional bay also with a static fault, this time on the phase B. Injecting and seeing again a trip of the device in 300 milliseconds. Getting back to the nominal values and quitting the alarm. And the second test we can see is that it's working not only for the conventional values, but also for the inputs that are typically coming from process bus. In that case, where I will inject my static values is at the merging unit, where I will simulate this time a fraud over the three phases. And you see I injected on the merging unit. I got the result on the protection device. Again, a trip, this time showing the reaction on phase A, B, C, as I injected a value for the three phases. So that way, we can already simulate plenty of applications, protections applications, but also or control applications or testing binary inputs. If, for example, for the merging unit, I want to simulate, change the position of the circuit breaker or of the disconnector, I'm getting the values reflected immediately in the display. You see I changed now disconnector 2 is open, disconnector 1 is closed. It was the other way around initially. So those are the possibilities via static injections of current, voltages, and binary input. Now let's go back to the slides and see the next possibility of testing transients this time. It is using the ComTrade replay functionality. ComTrade is a standard format that can be either retrieved from a real protection device after a power fault or can be generated by a software simulating a power system. You simply extract that file from the software or from the device, map virtually the traces to physical virtual hardware terminals of the protection device and be able to replay them. So let's see again in my browser, how does it look like? Back to my browser where I injected the values. Let us clear the last power faults we created. And if I want now to integrate test files, you see a tab called test files to manage various state files, the ComTrade, and the state sequencer also that we will see a bit later. In that editor, it's possible to upload your test files by browsing the files on your local machine. I've already uploaded a ComTrade file for my test. That ComTrade file, if I don't remember why is it the content, because the name was poorly given, I have the possibility to visualize it in the browser, seeing what was that test I want to replay. And here you see on phase B, we are simulating a fault after the pre-fault of 500 milliseconds. Phase A and C are normal. That ComTrade file now, I can route it to one of my devices. For that, I have a powerful editor called the routing matrix that is used to configure virtual wirings between binary inputs and binary outputs of devices, as well as test files. So let us map the ComTrade file, the source file for the voltage, to our CProtect 5 compact device, or the 7A685 device. Here, I'm configuring the first analog trace to phase A, phase B, phase C. I replicate the same for the currents to phase A, B, C, and the neutral. And that ComTrade file, I can also map it not only to one device, but to multiple devices. So you remember that protection device is protecting two bays, one conventional bay that we already mapped, and the ones with the merging unit, where we will also inject the same values on the merging unit for the currents and for the voltages. All that work is usually what you do with physical wires, with test equipment, and here the same applies, but in a virtual environment. Once those test files have been wired, simply go back to the editor where you see the devices. Again, we quit the existing trip indications. And in that interface, we have the possibility to select now the ComTrade file we want to replay for that device. That device, now I can simply replay it. And as you see, the device is tripping on phase B. It is correct. We've seen the ComTrade file was having a fault on phase B. And you see at the top of the screen, two faults have been created. One with the names bay process bus. This is a protection function that was protecting the second bay with process bus. If I quit that alarm, remain the second fault that was cleared by the other protection algorithm protecting the conventional bay. So same behavior as earlier, but with dynamic values, we are generating the trips, and the evaluation is done then in a so-called open loop testing, that you are reading the value out of the display of the device, or you are downloading the data from that device via the DXC for further investigation. So now let's go back to the third option existing in the presentation. After the static injection, the ComTrade injection, now let's go to the state sequence injection. In the state sequence injection, it is also a very common test scenario for validating protection, the behavior protection devices. The similar procedure exists as for ComTrade. It is about mapping current voltages, binary inputs if required, and the particularity is that you need also to configure triggers based on which the device will jump to the next state. And how to engineer those state sequences? We are providing two options today as XML input files. One is a Siemens XML solution that can be created via an Excel plugin. And the second one, if you already have a test realized in other tools that provide also XML interfaces, we are supporting the Omicron Test Universe export, where the test can be later also reused exactly with the physical device on site with a real test kit, that the preparation work is still validated on site. So let us see that part also with a demo. So back to the screen where I was earlier. I mentioned the test files. We can upload various files. We did it for the ComTrade file. Same procedure is possible for the state sequence file. And for the state sequence, I already imported it also to prepare that webinar. You see the file here. And now that file needs to be mapped to the virtual terminals of the device. The same procedure, we do that in the routing matrix. We select what we want to route. Let us start with the voltages. I select the source file, my sequencer demo file. I select the device I want to connect to. So this time I've connected it only to the protection device, the first bay protected in conventional way. I do the same for the currents, configuring phase A, B, C for the current inputs. And important now the other direction that we want that trigger to be configured. So the trigger is a binary signal to be selected. And I need my protection device to send that trigger to the sequencer. You see the sequencer is providing me a virtual input called trip, and I'm connecting that when a trip is occurring in my protection device, it is then acting as a trip signal, jumping automatically into the next state. So now that we have prepared that virtual wiring, let's go back again to the device simulation. And this time, instead of selecting the COM thread, we select the state sequence file. Select it, replay. And what is happening, you can observe in the orange bar that the current state replayed is displayed that we are currently in there were 4 states. And the device followed all the steps based on the triggers. And at the end of the results that we see on the screen is there was a trip, another current definity to trip, 100 milliseconds, which was also the value configured into the device. So you see those 3 options to validate process input data in an open loop format, how they can be performed. So let us jump back to our slides to see the next typical request we are getting from our customers when we're discovering the potential of digital twins. So many users are typically asking, what else can I do besides having those devices in the cloud? What about physical connections to existing equipment, such as a physical RTU, a computer HMI, or even a physical IAD involved in a goose interlocking scheme with some virtual devices? And this is possible to interconnect, to bridge those 2 worlds, the physical world of a test lab and the virtual world of the Ciplex digital twin with multiple devices. So how does it look like again? So for that, we'll show again in a short demo how we can interface different communications. We'll see 3 of them. One being the connection to the Dixie5 software located on my computer and interface via the VPN. The second one will be connected with the IC350 test client simulating MMS communication, and the third one with our web UI application from the Cyprotec relay. First, let us then connect to the Dixie. So you remember at the beginning the sim files that I used to simulate, to generate the simulation file used in the digital twin was coming from a Dixie project. So here's my Dixie project with the 3 devices I was using. And now I would like that Dixie project to interact with my digital twin and, for example, retrieve the latest log out of the device. So for that, I need to connect my computer via a so-called VPN to our digital twin environment. Then connecting the background. Wait. Wait. Okay, so second attempt is now connecting. And now that it's connected, my Dixie can interact with the digital twin. So for that, let's go to the device that generated some trips, the 70685. I'm going to the process data of the device, and I want to get the fault record. For that, let us read the records out of the device. Dixie is establishing the communication with the device the same way we do it with a physical protection device. No different there in the user experience. And you see that plenty of fault records have been discovered. We have already simulated plenty of faults into that device with a static injection, with a COM thread replay, with a state sequence replay. So let us just download the last file we got from the device. It is now transferring to my Dixie software, and I can now read it in Dixie. The same could be done for any other online application, such as reading also the fault logs of the device, or also be used for online CFC troubleshooting. Here you see the latest fault logs that we've just generated are then protocoled here. So in similar line, that's what we can do with Dixie. We can have it also with a 650 test client. So here I am starting our IC browser, which is just an MMS connections to the device. This is the IP address of my device. And it is browsing the complete data model of the simulated device into the digital twin environment. It's possible then to see the complete model with logical devices, but also logical nodes or data objects, data sets. So all the functionalities from 650 are there available. I would receive also the Goose telegrams sent by the virtual device, or I would be able to send Goose from my computer or from a physical device as a bridge over to the simulated device in the web browser. So in that way, it's possible to fully test a substation automation system simulating any signal of a protection device capable of supporting digital twin. And the third example that I'd like to show is also the possibility, not of further communications protocols such as DNP, Modbus, TCP that are also supported by the digital twin environment, but our web user interface from the device, where I'm again connecting to the IP address of the device. And while connecting to that device, I have the possibilities to reach out the many functionalities existing in it. So either to read also the fault records of the device, or getting detailed information about the logs, or seeing the settings of the device. And for example, we mentioned the protection function that was earlier tripping. The overcurrent protection is, you can see all the settings in that web interface. You have the possibility to change them. This was the one that was tripping earlier with the value 1.5 secondary value, and things, the protection characteristics of that function, where is the operating point with the dotted line that is helping you in the troubleshooting in case your test result is not the expected one, because either a function was per inadvertence configured as deactivated, or a threshold was not properly entered. You can see it and change it easily there and retest and get the expecting result. And so now that we have seen plenty of possibilities of the standalone environment with the Cybertech Digital Twin, let us go back to the slides, see what more can we even offer with that solution. And this is where we are coming to the really most expecting part of the webinar. That was the title of it. How we have made a big jump, bringing the virtualization to the next level from an open loop testing environment to a virtual closed loop environment using open APIs. An API stands for Application Programming Interface. It is using secure communication via HTTPS, and it enables test automation with automatic test assessments of the results by providing the binary outputs result of the digital twin to any partner application. And for that, I will hand over to Florian with that promising quote from one of our early adopters, the market, combining both digital twins of cProtect and relay sim test. And Florian, the stage is yours.
Yeah, thank you, Cedric, for this nice introduction to the digital twin. I now take over for the part of relay sim test. So we, as Omicron, made use of this API interface to interact with our simulation software relay sim test with the digital twins. So I make use of the digital twins to test a whole protection system in a virtual environment. But before I start with a demo, I just want to give you a brief overview about relay sim test. What is relay sim test? Relay sim test, first of all, is a software that's able to control our CMC test sets. And maybe the one or the other listener already knows Test Universe from Omicron. So we already have one software that's able to control the CMC test sets and to inject currents, voltages, binary signals to a protection device to be able to test it. And we call this testing approach a settings-based test approach. So that means what we do there is we really ensure that the relay is working according to its settings. I will give an example. If a setting of the overcurrent protection function is set to the overcurrent stage, maybe to 1.5 amps, then we use, for example, a ramping module and ramp up current to see if the relay really trips at 1.5 amps or maybe at 1.6 or 1.4 amps. That's what we do with Test Universe. That's called settings-based testing. And I've brought with me this ERO misoperations study where you see the causes for misoperations in a substation. And in the study, there is shown that 20% of the misoperations are due to relay failures or malfunctions of the relay. So that would be something we could check with Test Universe when we inject currents, voltages, if the relay really trips or not. So if the analog converters are working correctly, everything, maybe if binary outputs are broken or something like this. But as you see, there are also other parts that cause maloperations in the substations, like, for example, incorrect settings of a relay. So somebody calculated wrong settings, and these settings are set in the relay. When you test this with Test Universe, you will find no difference between the set parameter and the test result. So therefore, we need a second approach to test the overall protection system. And this also includes communication. So you see this 9% are also causes for misoperations. So you need to test the communication as well of a protection system. And that's often not done with Test Universe, but with our second tool, Relay Sim Test, that's now much easier because you can control multiple CMCs with just one PC. So in the end, we have this overall picture between Test Universe and Relay Sim Test, and it's a complete puzzle. We call that it's our protection testing overall context, and we call what we do with Relay Sim Test system-based testing approach. That means we really ensure that our overall protection system is working correctly. So whenever there is a fault, for example, on my line, that it's cleared maybe within a fast trip time. Yeah, relay sim test, how does it work? Just a few remarks to that. I will show that later on directly in the software. The focus of relay sim test is on the power system. So that means, like it's shown here, you try to simulate part of your power system, like it is done here with a in-feed element and bus bar, circuit breakers, CTs, VTs, a line, and at the end of the line, a load. And there is a relay connected to the CTs and VTs. And then maybe we place a fault or we simulate a real world test case. So that could be that a circuit breaker opens or closes or that a fault appears. We calculate the transient signal. So here it is shown the voltage of the relay that's measured. So we have this pre-fault condition, fault condition, and post-fault voltages. We inject this, also the currents, to the relay, and then we measure back the reaction of the relay. So the focus is definitely on modeling the power system, then creating some real-world test cases, then run these test cases and assess then afterwards the protection behavior. And in the end, you will get the results in form of a report. Yeah, we can test quite a bunch of different applications with relay sim test. Here's just a small overview what we can also do with the digital twin of Siemens, so with the C-Protect digital twin. We could simulate auto-reclose sequences in a transmission on a transmission line. We could simulate series compensated lines, 3-terminal or even multiple terminal lines. We could simulate parallel lines with mutual coupling. We could simulate or test devices with teleprotection or line differential protection. We could simulate power swing events or out-of-step protection functions. We could also simulate phase shifting transformers and therefore then test the transformer differential protection of a phase shifting transformer. And in the area of substations, we could test busbar protection systems, transformer differential protection. We could simulate different kind of networks, so insulated networks, compensated networks, different compensated networks, break and a half schemes. And of course, we can combine these applications. So we could also test distance protection function with teleprotection and an active auto-reclose function. Or we combine, for example, the transformer application with the line with the differential protection, so that we have a differential protection of a line with a transformer in between. And with relay sim test version 4.10, it's now also possible to simulate induction motors. I will focus in this webinar on the auto-reclose application and the transformer application. So there I will show you how to test an auto-reclose sequence for a line protection, and also how to test in a virtual environment transformer differential protection. Yeah, how does it work? The overall test setup. First of all, I think that's clear. You need a PC where relay sim test is running on the PC. And then the PC is connected to our test set, like in this case, a CMC 356. And the CMC is wired to the physical protection device. In that case, a Siemens distance protection device. And it must not be just one device. With relay sim test, we could also test with multiple CMCs and also test multiple protection devices at once. The problem there is, and there I have some pictures I wanted to share with you, is the overall test setup. I mean, that's not a typical test setup, maybe if you test a single protection device, but you see there a lot of CMCs, amplifiers, which were needed, for example, to perform an IC6255 test. Or on the left-hand side, you see a test setup of a busbar protection test on site. So you need a lot of hardware, test hardware, and also a lot of wiring. How does it look like in a virtual environment? I mean, that sounds clear, obvious, that you don't need the hardware anymore. So forget all about the CMCs and the protection devices for a virtual test setup. What you need instead is Relay SymTest version 4.20, so the newest version, where we offer the possibility to connect to the Cyprotec digital twin. And of course, you need the digital twin running in the cloud. And then we establish a connection via this API to the digital twin and interact with the digital twin. So Relay SymTest has this so-called iterative closed loop functionality implemented. So that means that we react with our power simulation on the reaction of the relay. So whenever there is a trip or a close issued by the relay, we will interact, stop our simulation, do a recalculation, open also in our simulation the circuit breaker or close a circuit breaker. And we can do now the same in a virtual environment with a digital twin. So whenever the digital twin sends a trip command, we will recalculate our transient calculation and open a circuit breaker in the simulation. And that's what I want to show you then in the practical demonstration. Here, a short overview about the benefits in general if you work with digital twins. I've mentioned that already. You don't need the hardware anymore. So you are independent of the test sets. So you do not have the limitation of the output power of our devices. So it doesn't matter if you use a CMC 356 or 256 plus or CMC 430 anymore. You have an unlimited number of test signals available in a virtual environment. And of course, you don't need the protection IDs anymore. So it removes the need for spare IDs for testing purposes. You can test intensively, so with thousands of test shots without stressing your IED. You can switch between different IEDs without wiring or rewiring. So you can test within minutes and switch between a distance protection or in the differential protection device, for example. And you can switch between the different firmware versions. So you don't need to do a firmware downgrade or upgrade. You just choose the firmware version you want to test in the digital twin environment, and then you can start testing. And of course, you're independent of the location where you are. So that means if you work from home or if you're sitting in the train or at the airport when you have a business trip, that doesn't matter. The only thing you need is a stable internet connection. Yeah, what are the benefits now, especially of Relay SymTest using this digital twin feature? We see there two promising benefits. The first one is you can validate your protection system now very, very early in the protection life cycle. So when you are during your engineering process, you can already start to test without the hardware and find there maybe then the first design errors. You can create real world scenarios and replay them already on a digital twin. And of course, therefore, you shorten the commissioning and the testing time in the field afterwards. I don't want to say that you don't need to do the tests in a physical environment, so really in a substation. I mean, that's clear. The digital twin really helps in that early engineering process phase. And then at the second point, you can already pre-check your test plan and increase, therefore, the test quality. So what I mean there is you can create and develop already your test plan, set it up, and then run the whole test plan with a digital twin. So if needed, then you can adapt test cases. Maybe you did some wrong measurements, you forgot maybe a binary signal that you need for the test. So you can adapt whenever you need your test plan. Then you could also find errors in your protection system test plan, and you can reuse exactly the same test plan that was used now in the virtual environment for the physical IED testing afterwards. And with this said, I want to jump in a live demonstration. So what I want to do now is I start RelaySimTest. I switch on my PC. So I have started there already one file where I have created a power line with a length of 32 kilometers. It's fed from two sides, infeed A and infeed B. And two relays protect this line. So that means these relays are really connected to the CTs and the VTs and issue their trip and close commands to the circuit breaker. On the other side, the same. If I go into the relay, you see that I have connected the three-phase VT and the three-phase CT to the relay, and I have already defined some binary signals, so a pickup signal, a trip, and a close command. And I have also the possibility to simulate the auxiliary contacts of the circuit breaker. Therefore, I want to simulate the 52A and B, so the open and close contacts, the auxiliary contacts of the circuit breaker. And I make use of a CB ready signal to start an auto reclose sequence. So my digital twins are configured in a way that they protect the line with a distance protection and with an auto reclose, with an active auto reclose function. When I have done that, so that's quite normal test setup, I will now insert the digital twin connection. And now with this digital twin connection, you see the test set configuration gets minimized, and I can switch with one click between now a physical environment and a digital environment. So I will work now in this digital environment. I have already created my test plan. So I will start with a wiring check and afterwards test an unsuccessful and a successful auto reclose sequence. So I will open the test case. Then you see my power system, and here in the time signal view, you see the voltages and currents measured by both relays, relay A and relay B. So here you see the signals measured by relay A, my binary signals of relay A, and here you see my time signals of relay B. Okay, my preparation is almost done on RelaySimTest side. What I need to do now is I need to prepare my digital twin. I could press the play button and then I get a list of tasks, what I need to do on Siemens side to prepare the digital twin. First of all, that's clear, you need to log in to the digital twin. I have already done that. And as Cedric explained before, you need to export from Dixie a SIM file and to import it in the digital twin environment. I did that already. I have here a list of different relays. I will use relay A and relay B. The next step is I need to upload a state sequence XML file. And in this file, there is all the information stored of the different analog values, the binary signals, which I use for my test in RelaySimTest. So I will do that now. I upload or I save this API reference file on my PC. Then I jump to the digital twin, go to test files, and import now this API reference file. Okay, and in the next step, I go now to the routing matrix, and I need to do the more or less virtual wiring of my digital twin. So that's what's shown here. Create and upload the state sequence XML file with exactly the name, API reference file on the test file page on the digital twin web interface, and then map the devices in the routing matrix. So that's what I will do now. It seems that I need to refresh. Okay. Yeah, that was the last uploaded API reference file. Now I go to the routing matrix, and I always start with the voltages, then with the current, and then with the binary signals. So I choose my digital twin relay A, and now I do the virtual wiring. So you see there in the rows all the signals I have defined in relay SimTest. So 3 times the voltage of relay A and 3 times the voltage of relay B. I connect them now to my virtual analog inputs of the digital twin. Then I do the same with the currents. For relay A and for relay B. And last but not least, with my binary signals. So these are the binary inputs of my digital twin. So the 52A and B contacts of my circuit breaker. I need to connect them. And the CB ready signal, as well as for relay B. Close the open position and the CB ready. And now I need to configure in a last step my binary outputs of the digital twin to my relay SimTest file. And I use there the trip command, the close command, and the pick up for relay A, and the trip, close, and the pick up of relay B. Then I'm done. Then I can power on my devices. So I choose relay A and relay B, and then I start up the devices. So digital twins are preparing, and I use the time now to split my screen so that we see both in parallel relay SimTest and the digital twin running side by side. So I stop there the test execution so that we can have a look on my first prepared test case. What I wanted to show is in the first test case a virtual wiring check. So to be sure that my routing was done correctly, and I simulate there my circuit breaker ready signal that the relays are able to perform an auto reclose sequence. And you'll see there a simulation duration of 30 seconds. That's enough time to read the measured values on the relay display of the digital twin. And you see there in the widget view also the calculated values, the steady state values. So the display of the digital twin should show 63 kV as the voltage and 191.5 amps current flowing on this line. Okay, it seems that we have, or I have with my computer some connection issues to the twin. Okay, start the twin again. While the twin is starting, I can show you the next test case then, which I have prepared. That's the unsuccessful orderly close sequence. And it's unsuccessful because I do not give the signals to the relay that my circuit breaker is ready to perform an orderly close sequence. So for relay A and relay B, I open the binary contact, the CB ready contact. So what do we expect in the test case when there is a fault, for example, at the end of the line? So first of all, there is the normal load flow. Then there is a fault happening at the end of the line. And we expect normally that the relay A will trip for this fault and also relay B, but relay B in a much faster time than relay A. So let's see if the twin has started up already. That's not the case. So then I will jump to another file where I have already prepared results. So when you open the sample documents, you will find there with transformer protection different kind of sample documents. And there is one with a 3-winding transformer differential protection. The one is executed with a physical device, and the other one, exactly the same tests, were executed with a digital twin. And I will open now this digital twin. And you see now it's a completely different application. So there you see the transformer that's protected by this transformer differential relay. It's connected to all of these CTs. And we simulate also the tap changer of the transformer. And you see also the digital twin connection is established. And I have performed there quite a few tests. I will not show all of them in detail, but maybe we jump to the inrush. What I wanted to simulate there is I want to power on the transformer. So first of all circuit breakers are opened, and then we close the circuit breaker on the high voltage side. So the transformer gets energized. And what typically happens is that for such a kind of a transformer, you will measure an inrush current. And you see now the calculation of this inrush current here. That's a typical waveform of an inrush. And I want to see that now my protection system stays stable during that inrush condition. So what I did, I performed the test, and you see there the relay measured a current on the high voltage side and no current on the low voltage or on the third winding. So therefore, it said, okay, there must be a differential current, and I pick up. But at the same time, the relay blocked the differential protection and said, no, that's an inrush. I detected an inrush, so I blocked the tripping. So this test was passed then, and you also see the inrush detection was not just an inrush detection by a second harmonic content protection function, but by also the CWA protection function. That's a special algorithm Siemens introduced with the 65 relays. So Siemens is not just looking on the harmonic content of this inrush current, but also on the wave form of this inrush. So you see here these flat areas, and the algorithm detects these flat areas and says, okay, that's an inrush, a typical inrush condition. We need to block the differential protection function. And you see, this inrush is not a replay of a comp trade. It's just the calculation when you simulate the saturation of this transformer. And then another test case here in the trip test, if I perform exactly the same scenario with an inrush on the high voltage side, but now after a certain time a fault occurs, what happens then to my protection system? That's an interesting question. I mean, everybody of us related to some protection testing should know that of course the relay should trip, because first of all, there was the closing of the circuit breaker. Then the algorithm decided to block the trip. And then when there was a fault event happening, then the relay started to trip, and the blocking of the inrush detection was immediately stopped at that time. And you see the test is passed because that's what I have expected from my protection system, or in that case, from my protection relay. Okay, that was the showcase of the transformer application. I now want to jump back and see if my digital twin is working. I think I have connection problems with my guest Wi-Fi there. The question is if I can start again. Maybe I closed this window. Yeah, I lost the internet.
Am I audible?
Yes.
Okay. So, yeah, live events, this can happen, always challenging. So let's give Florian some time to reconnect to the Wi-Fi, and we will use the time, or I will use the time together with Cedric to answer the first digital twin related questions. Maybe we do it like this. Okay. So we actually do have a lot of questions. Thanks for that. You will definitely get some homework. And yeah, I want to start with a question from RA about is it possible to do a switch onto fault test with the digital twin? Maybe this is also good for the interaction between relay sim test and digital twin, right?
Yeah, most of the applications that can be tested that just require the standard analog currents and voltages and barrier inputs can be tested. Today, the only limitations we're having is for applications where we need also to connect 20 milliamps values. Let's see, we have not tried that application yet. So the combination of Cyprotec Digital Twin together with relay sim test is quite new. We released it in June. So it has not been a core functionality, but I would expect it to work. Let's try it together.
Or it's up to you to try it out. Okay. There's another question, Cyprotec Digital Twin related, from GK. Will it be possible at some point to run the digital twin locally, in example on a Linux system? So are there plans to do that, or is this always planned as cloud application?
Currently, there's no plan for that. Currently, it's a software application in the cloud, which is one of the strengths also to deliver those new functionalities, those open APIs that are common from SaaS applications in the market. So it gives lots of opportunities. There are also some challenges associated to it, but currently the point is to continue with the cloud application.
But I think there are also a lot of benefits to doing it like that, because you don't have to update anything. You will always get the newest version, always the newest firmware, no updating necessary, and so on, right?
Exactly. This is very agile. So every month we're having 1 or 2 releases with features or bug fixes. The security is also handled in a cloud environment. So instead of following processes in the company, we're taking care of the data, like the multi-authentication during the login and plenty more activities.
Okay, then I want to jump to a question from DHE. On the digital twin screen, can we see the front display on 2 simulated devices at the same time?
Yeah, good question. Indeed, you've seen during the demo, currently to fit the screen width, it's one device at a time, where you need to collapse one device and display expand the other device. It's indeed one of the feedbacks we're getting from a certain number of customers. So we will check what could be done in that direction. But today it's one device display that you can see at the same time, and switching from one device to the other, depending on what you want to investigate.
But maybe you can have like the display of one device in the digital twin and the web browser of the other device, open the web browser of the other device to check both relays at the same time, maybe?
Yeah, exactly. Depending what you want to see, or what was Florian presenting, splitting your screen with multiple applications. Yeah. If you combine with a web UI application and you are just interested in seeing the values, the measurement values of the devices, indeed, you could have multiple web UI windows also open on a bigger screen. As a workaround for that.
Yeah. Okay, then we have like really many questions pointing in a similar direction. And yeah, the customers are interested in license models. I think this is also interesting for both of you, but I ask this to you first. So
okay,
can
I'll start
you,
it first. Later, Florian will be also glad to answer it for the relay sim test. But for the CPREC Digital Twin, we're having different licenses. So you see it at the end of the presentation. We are planning. There is first important to know a free trial version for 3 weeks to try out the product, and then when you like it, need it, we have a subscription model with 3 different licenses: a small one, medium one, a large one. Whereas the major differences are either the number of devices that you can simulate at the same time, that is being either up to 2 to 5 or to 20 devices at the same time. And from the medium license upward, what we have the possibility to have those transient simulation with country replay, state sequence replay, and also that new API functionality to perform the closed loop testing from the M or L license.
I have to say, I also tested the L license myself, doing a test for a big bus power system, and pretty impressive. Okay, yeah, just have a look. Florian, how does it look? Yeah. Yeah, then we stop this short first Q&A session. I hand over back to Florian, and we will continue with questions after Florian finished.
Can I see my screen, please? Okay, so sorry for the inconveniences. Thank you, Cedric and Nina, for taking over. I had to reboot my computer, so it was not a problem of the digital twin. Somehow my IT restrictions have forbidden me to connect again to the Siemens guest Wi-Fi. So my digital twin now started up. You see I have the relay A and relay B. So I need to switch between A and B, as one customer already recognized. We cannot show both displays at the same time. And on the other hand, now I have my relay sim test. Where was it switching now? Okay, here we are. What I need to do now is I need to enter the API password. And you can find the API password here in the menu. You create a password and you enter it here. And then you are ready, prepared to inject the first test shot to the digital twin. So let's just jump back. What was the first test shot? The first test shot was this wiring check. Where I simulate 30 seconds load flow more or less, and I give the relays the CB ready signal. So if you look at the display of the digital twin, you see that the circuit breaker is now in an undefined position, so not closed, not open, but undefined. And when I will start with my simulation, continue, you see we calculate the signals, then we upload the signals, and then they are executed on the digital twin. And you see now the LED is active, that the auto reclose sequence is ready, the circuit breaker is closed, and we measure a normal load flow of 191 amps and 63 kV. That's also what our relay sim test calculation tells us, 63 kV and 191 amps primary values. We could also see the same on relay B. That was the first test case. There was no trip, so the test was passed. Then let's jump to the next test case, an unsuccessful auto reclosing So I don't want to simulate now the CB ready signal. Therefore, I open my binary signal, my binary contact CB ready on both sides, on relay A and relay B side. And I inject this test case 4, so the fault appears at the end of the line, and we will see what happens. You will see now live the first injection. The digital twin reacted. We stopped our simulation and recalculated our signals. We inject now the second current and voltages, and the digital twin reacted again. So I will maximize now the relay sim test window to see what happens step by step. And therefore, we can look at the timeline. So first of all, here there was the normal load flow. Then I simulated a fault, a one-phase fault at 100% of the line. So there was a short circuit current flowing that was seen from relay A and, of course, from relay B. And then you see relay B detected immediately that there is a fault in front of the relay, and it issued a trip signal. After this trip signal was issued, we opened our circuit breaker on side B. So you will see that now it is closed, and in the next step, we opened circuit breaker on side B. For relay A, it took a little bit longer because the fault is at 100% of the line. So this relay A detected the fault in zone 2. So the trip was issued much later there. We could measure this time manually from the fault inception until the trip. We have here a time of around about 407 milliseconds. And there was no auto reclosing sequence. That's what we expected. Therefore, this test shot also passed. Now I want to show an unsuccessful auto reclose. So I simulate the CB ready signal for both relays. And let's choose test shot 2, so a two-phase fault in phase 2 and phase 3 at 0% of the line. We see the calculated signals there, and we start the injection. And you see the reaction of the digital twin at the same time. And that's done completely automatically in the background. So we adapt continuously our simulation. Okay, I need to do it once again. And I used a pause time between the different iterations because I want to ensure that the auto reclose sequence of the relay starts always from the beginning. You see, there are multiple iterations because the twin always reacts and responds to the simulation. And now we can double check what happened. There was a fault at the beginning of the line, a two-phase fault, and relay A and relay B recognized this fault and tripped the circuit breaker. So first, circuit breaker A was tripped, and after a short time, also circuit breaker B tripped. So that's what we expected. When there is a fault, both relays should be able to clear the fault in a fast trip time. What happened then? relay A and relay B issued a close command. So you see that there was a close command issued from relay B and also from relay A. Relay A was a little bit faster, so the first event was the closing of circuit breaker A. And after that, also the closing of circuit breaker B. But in between, circuit breaker A was already opened again because relay A interacted and said, okay, there is still a fault. You see, the relay could measure the fault current, the two-phase fault current there, and issued then a trip again. After that, the circuit breaker B closed, and after quite some time, also relay B issued a trip again. So you see the overall test of the complete protection system consisting of two devices protecting a line, and at the end you can do assessments if this behavior of your system is correct or not. And at the end I want to show one last test case that's now a successful auto reclosing sequence. That means that during the dead time, when before my relays issue the close command of the circuit breaker, I will stop the fault simulation. So I deactivate now my fault during that time, and we will see how my system reacts there. So I will choose this test case now, test case 5, show both the twin and relay sim test, and I start again the simulation. You see the relay issued a trip. We recalculated our signals, do a second iteration now, and so on, until the relay stays stable and there is no trip or close anymore. And let's have a look now to this test result. You see there was the fault, relay A picked up and tripped, also relay B. So we opened both circuit breakers on side B and on side A. Then there was the dead time that was set to the relay. We could also measure this dead time there. And then there was a close command from relay A and relay B. And you see afterwards the fault was cleared and there was the normal load flow again. So overall, this test is passed. My protection system reacted as intended. Okay, that's everything I wanted to show in this live demo. Now I switch back to the slides, because we often get also questions about how does it work in an IEC 61850 environment with the digital twins and relay sim test. And therefore, I have to say it's possible to test also in IEC 61850 environment, but you need to simulate your merging units also as a digital twin inside the cloud environment. So because we can just use this API and exchange ComTrade files. And so we have analog values, and these analog values can be subscribed more or less by the merging unit and converted now to a digital sampled value stream or a goose message. And then all the other digital twins can interact with this merging unit, and we can read back then the results of the merging units. So the digital signals get converted again to analog values, and we can read back this. So that's also possible. Yeah, and with that, I'm at the end of my presentation. If you want to have more information about relay sim test, please feel free to visit our webpage. Or if you want to have a deeper look into the topic of virtual testing and you are interested, please feel free to read our latest issue of our Omicron magazine. There is an article that I have written together with Cedric about virtual testing with digital twins. And Cedric will now conclude with a summary and an outlook.
Thank you, Florian, for your presentation and the very interesting live demo. So you've seen today that our first webinar with live demo showing the virtual ecosystem for protection and automation engineers, where both protection devices and system-based testing are combined together for greater benefits. This is seen as a game changer to the power industry to optimize and accelerate the project delivery times, increase the quality of it, and also attract new people using latest technologies. And important for all of you that get excited about that collaboration, that partnership with the Omicron release sim test. The API is an open API. There is a possibility also to interface more applications. So we'll be happy to further scale that ecosystem as an outlook into the future. And else, if you're ready to onboard, we had already one question around that during the intermediate Q&A session. We are providing free trials, both from the Cybertech Digital Twin perspective, as well as from the relay sim test. So contact us, get onboarded, and continue the digital journey with those new technologies. Thank you, presentation. And Nina, I think we got plenty of further questions.
Yes, we definitely have also some questions to Florian. Also more than you can answer in 2 minutes. Okay, so yeah, I want to start with a question from CR. And it says, will the interactive closed loop simulation be done in real time or stepwise?
No, it's done stepwise. Therefore, we call it iterative closed loop. So we do it in iterations. That was seen during my live demonstration. But that's enough to test protection systems. So whenever the protection system behaves exactly in the same way, you can do it in iterations, and you don't need this fast
real time or
a real time. Thank you. I was missing the word in a real time environment. Yeah.
Okay. Next question from YK. Maybe a question to the studio team. Can we also make the questions visible to my colleagues, please? Is it? Okay, perfect. So thank you. Next question from YK, right above the last one. Do you have developed variety of transformer models for relay sim test? For example, delta YG or Y star on both sides, so different models for transformers.
We have developed in relay sim test an open winding model, so called open winding model. There you have the possibility to manually connect the wirings of the transformer in that way that you need it. So we do not have a fixed then Y or delta winding. You are completely free in configuring your wirings.
Okay. Then next question is also going in the direction of license models. For example, from FQ, he asked, do I need a license for relay sim test? And maybe you explain also a little bit of the license model.
So relay sim test, first of all, is free of charge if you want to use it in an offline mode. So you can play around with relay sim test, see all the calculations, how currents are flowing in your power system. And if you want to inject then voltages, currents, or your signals to the CMC test sets, then you need a license. And if you want to use our more advanced transformer features, then you need an additional transformer license model. For the motors, we have also introduced a motor license. And for the digital twin environment, we introduced a new subscription model. So you need to pay yearly to be able to use Relay SimTest in the virtual environment, but then without any need for hardware licenses.
Understand. So I would say last question to you. It's a newer one from TL regarding Relay SimTest and Digital Twin. Can you export the results of the simulation, including the binary signals, for further analysis?
Yeah, we have a ComTrade export available in Relay SimTest. So each test shot, single test shot, can be exported via ComTrade to do further investigations, maybe with SIGRA or other tools. Yeah, that's possible.
Okay, and yeah, taking a look at the time, we are like almost finished, but I want to close the session with a nice compliment to both of you that I just found in the questions. It's from RG. And he tells us very good tools that Omicron and Siemens have developed. Here in Brazil, we made tests in busbar protection that was received a new bay. And we do the validation of the new parameters and logicals in the digital twin of Siemens and Omicron. And in the field, we just have to check the connections, the cable connections. So very helpful for protection engineers. Thank you so much.
Thanks, Ronald, for this compliment. Yeah.
Thank you very much.
And yeah, I think this is a good point to close the session. I want to thank, of course, our both presenters for the very interesting session. And I want to thank you for your attention. The recording will be available. You will get the access when with your registration link. And of course, you will also get the questions and the answers to all the questions that we had no time for the moment. And yeah, we hope you stay tuned and can welcome you to one of our other webinars later. So,
thank you for listening.
Thank you.
thank you. Goodbye.